So the next talk is going to be actually a series of 3 talks from myself, Tse Sreeram Kannan, David Shea, and Pramod Viswanath. And this hour is going to focus on how we can solve something called the blockchain trilemma. This is the result of our collaboration over the last year between the 3 of us and many more people. Okay, so what is the blockchain trilemma? Why should we be interested? So let's start with a high-level picture. So trust is a basic primitive in our society. And no wonder that platforms that deliver trust at scale essentially run the modern economy. If you look at Amazon Marketplace, Apple iTunes, Uber, they're all marketplaces which provide centralized trust at scale. The main friction with these platforms is that it is centralized. So the 3 vertices of the triangle are democratization, trust, and scale. If you look at the edge between democratization and scale, in fact, this is not new. So there have been decentralized services like BitTorrent, for example, which were very popular in the development of the internet, accounting for a large volume of the internet traffic. However, due to the inability to give trusted outcomes and incentives, they did not take off and were replaced by other centralized services. If you look at the other edge here, it is services that provide democratization and trust. And this is really where Bitcoin, Ethereum, and so on shine. So it's a breakthrough in providing decentralized trust, but not scalable. Okay, so that sets us up for the 3 axes of the problem. Okay, so what does it mean in terms of real applications? In terms of real applications, there are many potential applications that can actually be run on a decentralized trust platform. I've listed a few exchanges were the topic of the previous talk, but many other applications, but they require enormous scale. Millions of trades, tens of thousands of transactions, and so on. However, our core blockchain infrastructure is unable to support the scale required for these real applications. While there are many promising projects out there which try to close this gap, still, there is a huge amount of progress that is required. Okay, so this lets us phrase the key topic of this session, which is the so-called blockchain trilemma, formulated and at least popularized by Vitalik Buterin of Ethereum. So the 3 axes in the blockchain trilemma are decentralization, security, and scalability. And the trilemma asserts that it is impossible to get all 3 at the same time. No platform can be simultaneously decentralized, secure, and scalable. And indeed, this is borne forth. The intuition for this actually comes from the experience of trying to build these platforms. Platforms like Bitcoin and Ethereum are decentralized and secure, but not scalable. There are other platforms like EOS and Tron, which are secure and scalable, but not decentralized. And some others which don't have security proofs. So the question is it possible to get all 3? That's the main statement of the trilemma. Okay, so let's just look a little bit carefully at what it means by these 3 axes, because unless we define it, we will not be able to achieve it. So what does decentralization mean? Decentralization means that any writing access to the blockchain is controlled by some distribution mechanism, which could be the amount of compute power you have or the amount of stake that you have, proof of work or proof of stake. Security means that you should be able to defend against adversaries who are adaptive to the public state, and to be sure that you can comply with rational agents. What does it mean by scalability? There are really two different aspects of scalability, and they're nominally conflated. One is vertical scaling, what we call as vertical scaling. What do we mean by vertical scaling? The throughput, which is the number of transactions per second, or the size of the ledger, scales with the amount of resources per node. For example, if you provide a better network with lower latency, then the latency should go down. If you provide more bandwidth, then your throughput should go up. So this we call as vertical scaling, which is the throughput scales with the amount of resources per node scaling. But there is also a different type of scaling, which we call horizontal scaling. What do we mean by horizontal scaling? As we get more and more nodes in the network, the performance should improve with fixed amount of resources per node. So we call it as horizontal scaling. And computational efficiency. For example, each node can only process 1,000 transactions per second, but you have thousands of these nodes, so you should be able to process millions of transactions per second. OK, so that lays out the 3 axes for the blockchain trilemma. And the main question is, can we get all of these efficiencies, the scaling efficiencies, while preserving a decentralized and secure system? Okay. So that's the main goal, and our main claim is that indeed, we have an algorithm or a protocol called Trifecta, which achieves all these 3 properties. And what that means in terms of the picture we started with is you can have a new platform which is decentralized, secure, and achieves very high throughput. For example, in our implementations, we're already able to hit 250,000 transactions per second. So I'll let David first talk about vertical scaling.
Thanks, Graham. So is the mic working? Yeah. Cool. All right. Great. So when we started thinking about this problem, we focus on the vertical scaling. So as Sreeram mentioned, vertical scaling basically means that you have a fixed network with a fixed number of nodes, and you want to scale your performance up to the physical limits imposed by the network. But it turns out that our solution to this problem gives a very strong hint on how to do horizontal scaling as well. So that's why I'll spend some time talking about the vertical scaling solution, and then Pramod will explain how this could be extended to achieve the horizontal scaling. So this this protocol that was invented to solve this vertical scaling problem is called Prism, and it will appear in the ACM Security Conference in November in London. OK, so first, we go a little bit more detail into the physical limits. So there are basically 2 types of physical limits here. One is you have a distributed network, and this network is connected together by pipes. And these pipes have bandwidth limit or capacity limit. So let's say C is the capacity limit. So there's one example of a limit. So for example, if your pipe is 250 megabits per second, then C is 250 megabits per second. On the other hand, there's another limit, which is how long does it take for information to propagate from one point of the network to another point of the network, potentially through multiple hops. And this is a speed of light propagation delay, D. So these 2 numbers, C and D, are attributes of the network, but we're running the blockchain protocol on top of this network. And so these 2 numbers impose a certain limit. And so when we started off this research, we thought, OK, so any protocol can have a point in this 2-dimensional figure, transaction throughput on the x-axis, and confirmation latency on the y-axis. OK, so Bitcoin, for example, have transaction throughput 7 transactions per second, latency of the order of hours. So that's 1 point. And the capacity, C, of the network imposes a limit on how much transaction throughput you can get. Okay? If you only have 250 megabits link, then obviously there's a limit to how much you can push through, because this is a decentralized network, and transactions have to be exchanged between the nodes. On the other hand, the propagation delay puts a lower bound on how much latency you can get, the minimum latency you can get. So our research started off this picture and wanted to ask the question of whether or not we can find a protocol, okay, that goes from here, from Bitcoin, to as close to the lower right-hand corner as possible. That's it. So that's the goal. And I claim that we found one. And not only that, but we claim that the protocol we find is a very natural generalization of Nakamoto's longest chain protocol, which is the first blockchain protocol, so that we can simultaneously solve the scalability problem. So in other words, this is a way of moving the middle of the triangle to include all three vertices. So that's the claim. So now, in the next 5 minutes, I want to explain roughly how this protocol works, and I want to convince you that my claim is correct. OK. All right. OK. So let's start with the longest chain. So since our protocol is a generalization of longest chain, let me first explain how the longest chain works. So here, blocks are generated by the miners, and they get appended to the longest chain. And here, the blocks play two roles in the longest chain protocol. One is that each block contains transactions. And two, which is a little bit subtle, is that blocks actually vote for each other. OK, I don't know why it's not showing up here. OK, great. OK. Sorry about that. OK, so blocks, they actually vote for each other. So we know that in, for example, Dali mentioned, BFT protocols, a lot of voting is going on. Here, although the protocol looks very simple, and there's no explicit voting, but actually there's implicit voting, because what happens is that as blocks get deeper and deeper into the chain, then after a while, they can get confirmed. So that means that basically you're waiting for blocks to go down, and each block that get appended implicitly is voting for a block above it. So as you accumulate votes, eventually you can confirm. And the more reliable you want, in other words, the smaller the probability of reversal, the longer you have to wait. OK? So here we see the latency, and the throughput is controlled by one parameter, which is the rate at which the blocks are mined, the mining rate. And so a very natural solution to improve both the throughput and the latency is simply to increase the mining rate so that you get confirmed fast and your throughput is also higher. But as we all know, when we do that, then forking occurs. And forking is a problem because forking decreases the effective amount of work you accumulate on the longest chain, and therefore make you vulnerable to attack. And as people know, the more forking you get, the lower your security is. So basically, the punchline, to summarize this picture, is that forking reduces security. And this picture is kind of a very prototypical example of why the blockchain trilemma is difficult. Because as we try to scale the throughput, for example, we give up on the security. So in this picture, there seems to be some kind of potentially fundamental trade-off between scalability and security. And that may be one reason why the trilemma is difficult to solve. So what we discovered is that this trade-off is actually not fundamental, but is specific to the longest chain protocol. And what we did was we changed the protocol so that this trade-off disappears. OK? All right. So we start with the longest chain again. And what we realized is that actually these blocks on longest chain is doing too many different things. They're carrying transactions, and they're confirming or they're voting for a previous block. So our goal is to try to decouple these two important rows from the longest chain so that we can scale up each of them individually. So let me first start by figuring how to reduce my latency. And a way of doing it is the following. So instead of having one type of blocks, we have two types of blocks, the green block and the blue blocks. The original longest chain, the security is maintained by one structure. Here, the security is maintained by the blue blocks. So blue blocks are organized into many, many chains. For example, in our implementation, 1,000 chains. Okay? Now, all these 1,000 chains are maintained by all the clients. Okay? So it's not like each client maintains their own chain. All the clients maintain the entire structure. And these chains are the ones that vote for the green blocks, which at this moment carries the transactions. Okay, so transactions on the green blocks, blue blocks are voting. And because there are so many chains, the voting rate is much faster than before, about 1,000 times faster. And so therefore, you can confirm it faster. So that's the intuition. Okay? So this allows us to speed up the latency much faster than Bitcoin, much faster than longest chain. But as you can see, the throughput is still low because we need to maintain a very nice green structure so that the mining rate on the green structure is still very low. By the way, the mining rate on the blue structure, each chain is still very low to maintain the security. Okay? But the transaction rate is still very low in this example. So what we did is we applied the decoupling principle one more time. And instead of carrying the transactions in the green blocks, we generate a third type of blocks, which we call transaction blocks. And these blocks focuses on carrying transactions. Okay? And the green blocks no longer carry transactions. Their only goal is to win the lottery. And when they win the lottery, they will refer to a bunch of transaction blocks. So when a green block is mined, they will include the hashes of a bunch of transaction blocks they see. And when they win the lottery, their transaction blocks will be carried into the ledger. Okay? So now you can see that we can scale up the transaction rate without compromising the security of the structure. And the main point of this picture is the following. Security is maintained by the right-hand side. Scalability is achieved on the left-hand side. Why? Because on the left-hand side, now I can start generating many, many transaction blocks until I saturate my physical limits. In other words, my communication limit. Okay? So that's how we achieve vertical scalability and security. So we've broken the longest chain trade-off between security and scalability by having a structure that decouples the two together. Okay? All right. Can I have back to the slides? Thank you. All right. So this is a very nice picture. After 70 pages of calculation, we converted them into security theorems. We find that most of these security papers are at least 60, 70 pages long. So we thought we should, have comparable length to add credibility. Okay? And the theorems basically says the following. First, Prism is secure. We have not compromised security. The same 50% security or 50 minus epsilon percent security of Bitcoin. However, our throughput is much higher. Our throughput can scale to of the order of C throughput. Actually, it's not exactly C. It's C times the amount of honest power in the network. Okay? Because the adversary can still do DOS. But this is very high, much higher, so roughly of the order of C. And third, our latency we can achieve is the following. It's of the order of D, the propagation delay, which is the lowest you can get, plus a term which depends on the probability guarantee, 1 over epsilon. This is the typical security parameter that people see in these theorems, log of 1 epsilon, divide by a key parameter m, which is the number of voting chains. So for example, the picture I had was 10 voting chain. The implementation we have is 1,000 voting chain. And this m, you can actually choose quite large, because each of these voting blocks are very small. They only contain a hash, a pointer to the proposal block. So it's very small. And so basically what you can do is you can make m very large so that the latency is now very insensitive to epsilon. Okay? So just to dig that a little bit deeper, so the rough comparison can be summarized into this word. We achieve reliable confirmation via unreliable votes. So the left-hand side is the longest chain protocol. You have to wait for many, many votes to get deep so that the adversary cannot propose an adversary block that accumulates as many votes as you do. Okay? Here, what we do is we don't have to wait many deep because we have many, many voting trees. As long as they're, for example, 2 deep, okay, then it's very hard for you to change many votes. Because to change votes, you basically have to fork off many, many of these trees. And although each one is unreliable, that is, it's very easy to fork off, to fork off many of them, like 500 of them, is very, very hard. Okay? For example, if the reversal probability is 0.35 on each of these chains, to reverse, on the average, you can reverse 350 chain. But to reverse 500 chain is extremely difficult. And that's where the second term comes from. Cool. OK. So as I mentioned, we implemented this. And here are some results to convert the theory to actual implementation. So this is a paper we recently put on the archive. To give you some idea of where we are, this is a run on EC2 instances. And these experiments, we compare 3 different protocols on exactly the same experimental platform. Algorand, longest chain Prism. For longest chain, you can trade off throughput and latency. So the y-axis is latency. The y-axis is throughput. They're both on log scale. For Bitcoin, you can trade off by choosing the block size and the mining rate, and we do this trade-off. Beta refers to the amount of adversary power that you want to tolerate, 20%, 30%. Algorand, you can see the throughput is pretty constant. You can achieve beta equals 20%. That's the number they should fall. The throughput is of the order of 1,000 transactions per second. Okay. And finally, Prism, each of these points is only 1 point. There's no trade-off. For Prism, there's no need to trade off because we've completely decoupled security, the latency, and the throughput. So we can simultaneously get the best. But for different beta, you have different points. And we're getting throughput of the order of 75,000 transactions per second, latency of the order of tens of seconds to 100 seconds at high security level, 44%. Good. All right, so that's all I have to say. I'll pass the baton to Pramod. Thank you.
Thank you, David. So we talked about scaling, and the focus there was on vertical scaling. That is, for a given node, fixed number of nodes, but each node just got better. You bought a next version of your computer or a server from a laptop. And in the second part of this scaling, I'll focus on horizontal scaling. My name is Pramod Viswanath. I'm a professor at the University of Illinois, colleague with Andrew Miller, and part of this collaborating team. And we're focusing on scalability. So if I go back to these axes that Sreeram introduced, we're focusing on scaling, but on this horizontal scaling. What's this notion? That we fix each node's capability. So that means the resources per node is kept constant, but the number of nodes is increasing. And we would like the performance, throughput, to improve as you have more nodes. If you double the number of nodes, you would like your throughput perhaps to double. That would be sort of linear scaling. And the resources per node is kept constant throughout. Resources, I would like to think of storage, compute, and communication. And really the name for this kind of a scaling or performance in blockchain literature is called sharding. And what it really means is that if you have more nodes, keeping the adversarial fraction the same, your performance just becomes bigger. And I would like to emphasize this, sort of the three aspects to the resources per node is kept constant. And so these are three things that we'll keep in mind: storage, compute, and communication. Why is this sort of a hard thing? The key sort of phrase here is this is how blockchains are designed, which is this notion of full replication, which is that all nodes in the system maintain the entire state of the blockchain and participate in validating the state. So in this case, let's say in the longest chain protocol, you maintain the states. All the nodes maintain the entire network and participate in the validation process. So if you have more nodes, then that doesn't change. They're also doing the same work. And what improves is security. If you double the number of nodes, your security just got better. But they were not scaling in the sense that the throughput did not change. And one way to do is that if you double the number of nodes, I could say half the nodes, what were there before, maintain one part of the ledger, A. The other half, which you now have, maintain another part of the ledger, B. And so this scales in a way because now you have just half the number of amounts to keep track of. So you potentially get away with less compute, definitely get away with less storage. And but the security is now not increasing with the fact that you had doubled the number of nodes. Security stayed the same. And the key question, which is the key part of this trilemma, is that can you do both? Can you scale the throughput while also increasing the security? Ideally, you would like to have, if you double the number of nodes, you would like to sort of double the throughput and double the security. How would you do this? One way, a common way, in fact, that the literature proposes is this notion of randomized node allocations. So what you do is there is an outside the blockchain algorithm or sometimes inside the blockchain algorithm that allocates nodes to, in this case, two different shards, the left and the right, and purple and blue. And the ones in one of the shards maintain their part of the ledger, the other part maintain their aspects. And to prevent adversaries from specifically collating geographically in one part of the shard, every now and then you rotate this. So you reallocate nodes to shards and sort of redo this every epoch. And there's always a trade-off between how often you do this, because every time you reset, then you have to maintain a new state, bootstrap, get there, and work on it. So there's some trade-off between these two aspects. And this is considered a solution because now at least you would think that you can maintain less amount, so half the storage, but at the same time now at least not be vulnerable to, and the security is now perhaps scaling. But there are some problems associated with it, and I want to identify one at a time. The first one is that there has to be a way in which you allocate a node to a shard, which means you need to identify the node, which is a core thing. You need to be able to have an identity associated with a node to be able to allocate it. And this is different from blockchain, where anybody can be a miner, and whoever was a very active miner in 2018 is no longer active in 2019. So you don't need to be able to have a continuous identity to be able to participate in the network. This is one problem. Another aspect is that it's true that you're randomly shuffling and reallocating nodes, and that might protect against what you may call sort of static adversaries, which are a fixed number that they come in adversarially and they stay that way. But really, one can think of a little bit more powerful adversary, which what one would call adaptive. That is, they're not adversarial to begin with, or maybe they are adversarial, but at some point they may go and co-allocate after they have been assigned to the nodes. One way to think about it is that you know which node you've been allocated to, and it's not like you're adversarial to, or you need to be shaken down to become adversarial. I'm ready to be bribed. So I could go and sign up on a web page that I've been allocated on this shard, and there could be collusion among the people within the shard to be able to corrupt that part of the ledger. And so this is another vulnerability. So, and even if you're sort of shuffling the nodes, it's still vulnerable, because after you've been allocated, then you could pick up the nodes. And so this is another issue. So there is a security. So shuffling is not going to be OK if your adversary can adapt to where you are. The third thing is that even if you allocate just randomly, the fact is, if you want to have many, many shards, then you'll only have a few nodes per shard, and it won't be sort of proportional. So if you had, in this case, 4 out of 10, or so something like 40% adversarial power, it's not like it's maintained the same in every one of the shards, simply because the numbers are smaller. So if you want to maintain the proportion, then you really should have very few shards. And this is sort of a problem 3, where inherently, even with random allocation, without worrying about the adversarial, the adaptive aspect of the adversary, you really need to have large enough sizes to be able to have proportional representation of the adversary. And this is really at the core of the trilemma, which is that your efficiency decreases inversely while security decreases inversely with the number of shards, whereas efficiency increases linearly. So this is the sort of the trade-off. And how do you solve this? While doing, that all means you want to have both of them, throughput and security, while keeping track of the resources all being efficient, the storage, the compute, and communication. The key really is to maintain all 3 resources efficiently. And I'll try to give a quick overview of what we mean by that. So let's try to say that, let's focus, there are 3 things I said: storage, compute, and communication. I'll focus on storage and compute here, and Sreeram will pick up again with the communication aspect. That's sort of the more subtle part here. So suppose I look at compute and storage and think of them as sort of separate. That means one of them, maybe I'm willing to be inefficient, and the other one I'll try to focus on being efficient. So let's say that everybody in the chain maintains the ledger. So storage is not scaling. So it's just having more nodes, just being replication from a storage perspective. And I would like to be able to not allow everybody to validate. So how would this work? So let's say a node comes in, and it's blue, so it's not yet validated. And whoever gets that blue node could go and ask a random fraction of the network and ask them to help me validate whether this node that came in is fine. And because it's asking a random fraction, and it could take some kind of a majority vote. Everybody has the ledger, everybody has the full state of the network, so that they can actually do the validation for you. It's still, you have to ask enough people, and you should have enough network neutrality so you're not eclipsed. But this is a way of scaling compute without, everybody doesn't need to validate. Only the nodes that you're asked will validate and send you back. And because you have many nodes, you can get by with this. But it gave up on storage. So that's how you would do with this one. So how would you do with storage? So this time, I don't want everybody to maintain the entire ledger. But perhaps validation, we'll figure it out how to, maybe that will sacrifice something on. So if different groups have their own shard, how do you ensure that adversarially, I would like to be able to scale security? That means even if the adversary is sort of specifically focusing on one of the shards, that shard is still secure. Well, the only way is if that information in that shard is also contained somewhere else. And in a very notion of a shard means you divided it atomically. And the correct way to think about it is to have parts and bits and pieces of the data spread everywhere. In other words, you code the ledger and mix it up. And this doesn't seem in any obvious way how one might want to. So coding at least will ensure that even if a fraction of the shard has been sort of taken over by adversary, that as the data that was contained inside it is there in some coded way in other parts. It's not immediately obvious how one would do an validation, but we have a protocol that we call polyshard that allows storage to be scaling and security to be scaling, but only for some limited notions of what functions you can validate. You would like to be able to code and validate at the same time in a distributed way. So right now, we have been able to sort of validate low-degree polynomials or low circuit depth functions, which are not, if you have the goal of doing universal computation or like something like a Turing computation, then this is not the kind of approach you would like to take. And what we really want to do is sort of both of them. So computational efficiency, there are relatively clean ways. Everybody has the state, so they can validate. You can ask randomly. If you would like to store, just store efficiently, it's not immediately obvious, but that's something we've worked on. But really what you want to do is both of them at the same time. What I'll propose, this whole talk has been about trilemma, the trifecta is our protocol, the three of us. So there are really three principles at work about how one might go about with this protocol. So I'll state these principles. First one is that I don't want to be able to have an outside agent to do this node allocation. I want the nodes to be able to self-allocate which shard they go to and perhaps just stick there. So they come in, they pick a shard, it's out there, I pick a shard and I stick around. Okay, so this is sort of principle one. This will allow you, this will avoid the identity problem that I mentioned and allow you to sort of scale. You maintain only your part of the ledger. Okay, first one. The second one is that they're maintaining their own ledger, but they have to have some commonality to be able to share this, to be able to scale security. And the commonality here in with respect to the talk that David just gave are the proposal blocks and the voting chains. That's where the security was coming. They are relatively lightweight. They're just pointers and hashes. And so the transaction blocks are the ones that are sharded, that are kept separately, but they all link back. The security is driven by the core central chain, what one may call a sort of central chain, or in the context of Prism, the proposal blocks and the associated voter blocks. The issue there, though, is how does compute or a validation work at any one of these shards? Well, if every node needs to validate, then again, they need to know the state of the network, which is you're not maintaining all the shards. I mean, each shard has its own aspect to it. So that's not very feasible. So the decoupling principle is taken one step further by where what we agree on is not really whether the set of transactions are valid, like no double spend, for example, as instead of that, we'll just say that we agree on an ordered list of transactions, which may include perhaps double spends, but everybody's agreed on the same order. And there may be some communication needed, which will allow you to sort of separate out within a shard. If there's a double spend, then maybe you can go and delete one of them. But all the nodes have agreed on an ordered list. And so one can sort of state these things formally. That is, a shard could be entirely corrupted, but yet be secure. Because the security is not drawn by just the nodes within the shard, but they're all driving from this common aspect, which is the proposal and the voting chains. Second, well, if an shard is entirely taken over, then it may not be live because the guys inside the shard are not acting on it. But even if there's one honest node, the shard keeps moving. So in some sense, these are the sort of the strongest security properties one could hope for when you do this horizontal scaling. And we would say that its computation is efficient and storage efficient. They maintain just their shards, and they're only maintaining they're only agreeing with respect to an ordered list. The third aspect to this whole protocol, with respect to the resource, is communication. And each node is just maintaining its own shards, and it's talking about its own view of the world, you could say, and in some corner. And how do you even secure or know the security of what I am hearing if I don't even hear what's happening in the rest of the world? Because the security notice is drawn from all the people in the network, but you're not even hearing what they're talking. Maybe they're talking a completely different language. And so how do you know something has happened if you didn't even hear it? And without solving this, you don't really solve the entire trilemma. And that's the final part of this three-part presentation. So I'll hand it back to Sreeram.
Pramod described how horizontal scaling works in terms of scaling computation and storage. So here we will look at communication efficiency. So let's understand what this problem is. So let's say there are different nodes belong to different shards, here shown by the color. Blue nodes are all in a blue shard, and there are orange nodes and gray nodes. They are in different shards. So suppose there is a new block in the blue shard. Now, the rest of the nodes need to be convinced that the data is available, that this blue shard is available with at least one honest blue node. Why is this important? Because in the sharding scheme, we were writing in hashes of the block. Suppose you write in a hash of a blue block into the core chain, and the data is not available. Nobody has that blue block. Then the whole protocol stalls. So you cannot execute the shard beyond that particular position. So it's very important to understand communication efficiency, and in particular, data availability. How do you convince, in a given shard, I have a block, I want to convince the other nodes that this block is available? So we point out that availability is different from invalidity. If let's say a transaction is invalid, it is not temporally fluctuating, but availability is temporally fluctuating. So you cannot pin me down and say that, hey, there is no block, because then the adversary may release that block after you pin me down. So, okay, so let's understand how we can do this. So we're going to make a mapping in constructing a blockchain. For example, right from Bitcoin, there is a notion of a full node and a light node. So what we're going to think of is, think of the blue shard nodes as full nodes, and think of the remaining shard nodes, we call them out of shard nodes, as light nodes. And what we want to do is, the light nodes want to be sure that the block is available with at least one honest full node. Okay, so we have a full node and a light node, and what does the light node store? It doesn't store the block, but it only stores the headers of the block. And the data availability problem is, when you receive a header, you want to be sure that at least one honest node has this block. Okay. All right, so the notion of at least one honest node having a block seems tricky, right? How do you know that a node is honest or not? And here is where we make an assumption, which is now called in the security community as any trust assumption. The any trust assumption is basically that you assume that at least one full node you're connected to is honest. At least one full node you may be connected to 20 nodes, at least one of them is honest. That's all you know. You don't know which one. You're not assuming that a majority are honest. You're only assuming that at least one is honest. Okay, so how are you going to convince yourself that the block is available? The most obvious solution is to download the block, which is communication inefficient. If every node has to download every block from every other shard, then the communication resource is inefficiently used. Okay, so one idea is to randomly sample a block. What do I mean by that? Think of a block as being made of many distinct chunks. It could be transactions, but they could be partitioned into what we call as symbols. So what you do is you randomly sample some fraction of these chunks. Okay. So, and then if you got the chunks that you queried for, you believe that the block must be available. However, what an adversary can do is to simply hide only one chunk out of n chunks, n may be a million, and you have to sample a lot to really expose the adversary. So it doesn't work. Random sampling doesn't work because if only one symbol is hidden, it takes you a lot of sampling to expose that. Okay, so how do we get around this? So this idea here is, can we use codes? So what do codes do? Codes try to correct for errors and erasures, for missing symbols. So can we somehow try to use coding theory to compensate for this problem? So here is the main idea. You take the block, you take the symbols in the block, and then you somehow encode them to form an error correction code. Okay, so in this example, there are, the chunks now are M1, M2, M3, but also M1 plus M2 and so on. Now, what you do is the light node samples coded chunks from the block. Instead of sampling uncoded chunks, it's sampling coded chunks from the block. And what happens when you sample coded chunks is, if the adversary hid less than half the block, the remaining half of the block is sufficient to decode the entire block. Okay? So that's the main property of an error correcting or an erasure correcting code, is if some chunks are missing, you can still reconstruct the entire block. So all that we need to check is, instead of checking whether an honest node has the entire block, we can check that an honest node has half the block. Because if you have half the block, you can use the error correction property to reconstruct the rest of the block. So now, it is no longer a feasible strategy for the adversary to hide only one symbol. Because if you hid only one symbol, you can reconstruct that symbol from the rest of the symbols. So this is the main idea of using erasure correcting codes. Okay, so what have we done here? We started with, now we can easily assert that at least one honest node has half the block. Why? Because if you sample, let's say 10 chunks, and if the node has hid more than half the block, then you're going to easily find it out. So you know that at least one node has half the block. What that means is that one node can definitely decode the code. And what we would like to say is, therefore, you can say that at least one node has the entire block. But there is one issue with this, is the node making the block, which is in our case a blue shard node, making the block may not fully comply to your required code. May not comply to your to the code. For example, here, what it has done is it has taken M1 and instead of M1 replaced it by M1 prime when it created the header, the Merkle root. When it created the commitment, it used inconsistent symbols which do not comply to the code. So this is called the incorrect coding. This is called incorrect coding. And a node which does incorrect coding can potentially bypass our detection mechanism. So to deal with this, we have a mechanism called fraud proof, a coding fraud proof. What is a coding fraud proof? If a full node which has now decoded half the blocks tries to reconstruct the rest of the block, but detects that if you reconstruct the rest of the blocks, they do not quite add up to the Merkle root that was committed by the node. Now this becomes a provable fraud that that full node can prove to the other nodes. So this we call as a coding fraud proof. Okay, so here is the overall flow. So by randomly sampling a few chunks, we immediately know that at least one node has half the block. And what that means is either that node can decode the entire block, or it can tell you, provably, that the block has been incorrectly coded. So the difference between an incorrect coding proof and a data availability proof is that an incorrect coding proof is not temporally fluctuating. It is a hard proof. If you say that some block has an incorrect coding, it is verifiable and unchanging with respect to time. So this is the main idea of our communication scaling, is to use erasure codes to try to reduce the data availability problem into a coding problem. Okay? So instead of going over the details of this algorithm, I'll just state the main claim. The main claim is we have a new algorithm for coding. It's not as simple as just taking a regular erasure code and throwing it in. And we have a new algorithm that we call as the coded Merkle tree. We all know Merkle tree is a mechanism to commit to a bunch of transactions. A coded Merkle tree is very similar to a Merkle tree in that it has hierarchy, but it has coding embedded in the various layers. And when we use a coded Merkle tree, we can achieve not only a few bits that you download, but also, if you look at the third column here, it's called the coding fraud. The size of the proof required to prove a coding fraud is actually very, very small compared to other codes. We want to point out that this, there was a different code called the 2D Reed-Solomon code constructed by Mohammad Al-Bazam and Vitalik Buterin in a recent paper. OK, so that's our main result. So the main result is that you can use this coded Merkle tree in conjunction with our other ideas on vertical and horizontal scaling to solve the trilemma. So I'm not going to explain the construction of this code, but I just want to point out that the coded Merkle tree looks like this. It's just like a Merkle tree, but at each level, there is a coding and interleaving in order to construct the coded Merkle tree. OK, so now that we have described the various aspects of our solution, we had Prism to do vertical scaling. Pramod described how horizontal scaling can be accomplished by the three principles, and how I described how coded Merkle tree solves the communication efficiency problem. Now let's see if we can take all of these ideas and actually deploy them on a OK, so what am I doing here? I'm just spinning up a few Amazon EC2 instances running our algorithm, trifecta. So we just started 36 instances, and I'm setting up the run. So what we're doing here is we have 36 spot instances of Amazon EC2, which are loading the trifecta instances, which incorporates the various algorithms that we saw. And OK, and then I'm just starting the demo. All right, so the demo is just starting up. So what we see here is a bunch of nodes. They're generating various blocks. And if you remember the picture that David showed, he showed how Prism works. And in Prism, there is a core proposal chain, which is the green chain. There is the blue voter chains, which are trying to do voting on top of the core proposal chain. On the left side, David showed you that you have transaction blocks. When we implement sharding, these transaction blocks are arranged into distinct shards. You see here, there are different colors of transaction blocks, and they form the distinct shards. And when a miner self-selects, he selects which shard he wants to mine a transaction block for. But every miner is mining both the proposal blocks and voter blocks. And all of these are subject to a common mining process and a cryptographic sortition. OK, so as we're speaking, basically this is actually happening right now on the EC2 instance, 36 nodes mining these blocks in a distributed manner. So let's go and look at some more meaningful statistics here. So as the nodes are getting started up, we see that already in the last couple of minutes, the network has processed 4 million transactions. And the throughput is climbing up. See, it can go as high as 200 to 250,000. The confirmation latency is the amount of time it takes for a block to get confirmed. We have set our interblock time to be 1 every 10 seconds. So it's confirming blocks approximately in 2 to 3 times the network delay. You see the forking rate here, which is 0.002%. Actually, the current instances we spun up are basically in the same cloud. We've also done experiments where the instances are distributed geographically, then the forking rate climbs up a little bit to a few percent. So you scroll down, and we see in the dashboard various different shards. So in this experiment, there are 6 shards. There are only 36 nodes. But because of our particular nature of the algorithm, which is we do not use node-to-shard allocation and it's self-selection, even though there are only 36 nodes, we can actually have run 6 shards comfortably. And each of them are basically contributing to 30,000 transactions per second, which are adding up to the 200,000 transactions per second. So that's a very brief demo of our algorithm, Trifecta, and how it achieves all these 3 properties. With that, I would like to stop, and we will take any questions that you may have. Yeah. David and Pramod, you want to join?
Could you talk a little bit more about the voting blocks or the voting chains? I remember you mentioned, or someone mentioned, that every client maintains all of the voting chains, and if that's the case, how does that impact or improve scalability if they all have to maintain them all anyway? And how also do they, how do they vote?
So most of the computation and communication load is on the transaction blocks. One voting block is over 1,000th the size of a transaction block, because the transaction blocks contain all the content, the data of the blockchain. The voting block only contains a reference link to the proposal block. So it's just a hash of the proposal block. So it's very, very small. So although you maintain a lot of them, it's still a very small percentage of the workload of the system. So in our implementation, we have 1,000 voting chain maintained by every client. Oh, there are some questions at the back. Maybe we can.
Can you describe a little bit more about how these types of blocks are mining? So if you look at Nakamoto consensus, what they're basically doing is they're hashing the transactions that are included in the block and trying to find a nonce that meets. So in Nakamoto consensus, the mining process, the computation that's really happening is they're trying to find, they're hashing the transactions along and trying to find a nonce that meets the difficulty target. So in this case, you have 3 different blocks.
Yes.
So how are each of them mined? How are the transactions ordered in the transaction blocks?
Good.
And how is the voting done by the voting blocks?
So many questions.
How does it work?
But let me answer one of them, and then we can take lunch, and then we'll answer the rest. So the first one, how does it work? So you have a difficulty threshold, right? Let's call it tau, okay? Now, suppose I want to mine 2 types of blocks, just 2, just to keep notation simple. What I do is I have another threshold, tau over 2. If it's less than tau over 2, it becomes a red block. If it's between tau over 2 and tau, it becomes a blue block. So that's how I sortition into 2 types of blocks through the same mining process. For your remaining questions, let us take that offline, because people want to go to lunch and so forth.
Oh, we can take one last question. Yeah.
How does your construction compare to, on one hand, fruit chains, which have confirmation blocks similar to fruits, and parallel chains by Chaos, etc., which has this kind of confirmation of parallel chains? Is there some similarities, or how do you differ?
Yeah. So first clarify, first question, fruit chain, yes. You can view, if you look at just the transaction block and without a voting chain, our system is quite similar to fruit chain, except that the fruit chain main goal, in fact, their goal is fairness. Our goal is to maximize throughput. So that's the 2 different goals altogether. But the mechanism is indeed related. We mentioned that in the paper. The right-hand side is completely new, completely different. In terms of the relationship with the parallel chain paper, first of all, I should say that our work and their work is independent work. They both came roughly at the same time, and we have a lot of discussion with them. But you're talking about their solution basically achieves either good latency or high throughput, but not both at the same time. And we achieve both at the same time. I'm happy to go into more detail offline.
Thank you so much, everybody.